Very good evening. Welcome to today's live interactive session on geosynthetics and reinforced soil structures. So, today is the last and the 12th interactive session, and tomorrow morning at 9 a.m. for just an hour, we will be having a summary session where we will be discussing each week in approximately 4 to 5 minutes. So 12 weeks we will be finishing in 1 hour. So just a summary. We will revise. We will try to recall whatever we have studied uh, tomorrow morning from 9 to 10 a.m.
Hello, sir.
Yeah, yeah.
Sir, not audible, sir.
Not audible.
I'm not hearing your voice.
Hello. Now.
I'm not hearing your voice. Not audible. Please, sir.
Hello. 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 Hello.
Okay.
Just a second. Hello. Now is it audible?
Sir.
Audi
Okay, sir. Thank you.
audible, right?
Yeah. Okay. Thank you.
Okay,
Thank you.
okay, 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 okay. Just a second, check. Yeah, yeah. So as I was saying, that today will be our last and the 12th interactive session. That will be on landfills, design of landfills. Not we won't be dealing explicitly with the design of landfill. Just overall, we will just have an idea in what way geomembranes, right? Geomembranes are actually used, and what are some of the important properties of geomembranes that we should know, which is necessary for us to know when we have to use geomembranes for landfills. Okay, so in landfills, generally we use this geomembrane as liners, right? Liners. So here the geomembranes will act as a barrier, right? So we will see that thing, and tomorrow tomorrow morning from 9 a.m. to 10 a.m. we will be having a summary session where we will be discussing, we will just summarizing everything whatever we have studied in these 12 weeks, from first week to the 12 weeks, in 1 hour. Just in 1 hour we will just skim through all the topics, just try to recall whatever we have studied, that we will do tomorrow from morning 9 a.m. to 10 a.m. Okay, here only with the same link. So let us start. So what is a landfill? What is a landfill? A landfill is an engineered depression in the ground to dispose of different types of waste. So, landfill is nothing but a place where we dump all the waste, right? So, waste can be of many types, as we know. The most common waste that we encounter, that is municipal solid waste (MSW). Municipal solid waste, that gets generated from our households. It is the food items that we throw, then all the other things, those things that come in, those things come into municipal solid waste. Then we have hazardous waste. So these factories which manufacture, say, different chemicals or different substances, they actually release some kind of waste material which might be harmful if they come into contact with these living beings, maybe human or other living beings. So we need to safely dispose those things. So for that reason, we need these engineered landfills. So generally, previously, what used to happen in India, generally people, this municipal solid waste used to be dumped just without non-engineered landfill, just used to be dumped somewhere in a site. But nowadays, most of the places, these engineered landfills are used. So the main purpose of engineered landfills is that it gives a safe place to dump the waste. waste, maybe this municipal solid waste, say municipal solid waste or hazardous waste, industrial waste, whatever. So it gives a safe place to dump. So what happens? This engineered landfills. These landfills are actually engineered. That is, they are constructed in a specific way with the help of liner system. Okay, what the liner system does is that it prevents the leachate. What is leachate? Leachate is nothing but the liquid that is generated from the waste. Okay, that leachate to seep into the ground. So what will happen if that leachate actually seeps into the ground? What will happen is that it's going to ultimately disturb the natural soil, right? It's going to disturb the natural soil. It's going to change the chemical composition of the soil. Also, it might actually leach into uh, the groundwater. Okay, so groundwater must be spoiled. So to prevent that, we need to provide a barrier. So here this liner system is nothing but a barrier system which prevents the harmful substances that are generated from the waste to get into the ground. So this liner system, they are constructed with impermeable linings to prevent any leachate from migrating to the ground. As I said, the landfills are given a cap after they are completed and filled up with the waste. Okay, so what happens generally? There is a specified amount. Say we have in a landfill, there is a specified amount that you can fill only this much amount of waste in that particular landfill. So after we have filled the waste up to that specified level in that landfill, what we do, we cover the landfill so that we can seal the landfill properly. So this covered system, these are also designed so that what happens, so that the place which was initially landfill, that place can be actually reused. Okay, reused, and maybe actually, as we all know that there is a huge scarcity of space nowadays, right? Mainly in cities, big cities, metropolitan cities like Chennai, Bangalore, Hyderabad, Delhi, Mumbai, everywhere. So there is a space crunch. So in order to reutilize the space, what we can do is that we can cover the landfill, then we can engineer that cover in such a way that above the cover we can then fill again, refill with soil, new soil, then plant trees, grass, everything, and then you can just use that place again for some, say it can be used as a park or something like that. Okay, so that is actually the purpose of this cover of the land. And also this cover of the landfill also prevents these gases to directly pass. Okay, so we can install a filter system through which the gases which develops in the waste, that is actually passed in a engineered way. So I said, why do you need cover for landfills? So usually the landfills are spread over several hectares of land. The area over the landfills can be reclaimed by covering it in a scientific manner to prevent the ingress of rainwater or any surface water from it. So this cover actually also prevents the ingress of, that is the entry of water or any other surface water into the wastewater. Okay. Also to preclude the formation of unsightly scenes and release of water, prevent bird babies, etc. So what will happen? So if this landfill is open after use, say this we have filled the landfill up to this desired level. Okay, after that we will just keep that landfill like that. What will happen? It will just give a very disturbing sight, right? Very dirty sight. So it's better that we cover it up. Also to prevent bird menace, that means birds, these scavenger birds or some other birds, their tendency that they will pick up the waste, they will just litter it all around. So to prevent that, it's better that we design a covered system. Okay. So different geosynthetics are used in landfills. So first is the liner material. Okay, liner. So here the liner serves as the barrier, right? So the liner will serve as a barrier. It will prevent the leachate to pass into the soil. Alright. The liner. So mainly for liners, that is for the function of barrier. Two things are generally used. One are geomembranes and one are GCLs. So if you remember, GCLs are nothing but geosynthetic clay liners. Okay, GCLs. So GCLs, we have a clay layer in the middle where and this clay layer sandwiched between two other geosynthetic, maybe geotextile layer. So clay layer is sandwiched between two geotextile layer that forms the geosynthetic clay liner. Okay. Then we have reinforcement. So geogrids are used, geotextile are used to reinforce the slopes of the landfill, so that the factor of safety of those slopes actually increases. So geogrid, geotextiles, these are used. Then for drainage purposes, so to drain the leachate that develops into the this solid waste into this landfill, for the drainage purposes we can use geonets, textiles. And next is for protection. So geomembranes are this plastic kind of thing, right? So PVC plastic kind of thing. So to prevent the puncture of those, so it is very important that the puncture, that geomembranes are not punctured. So if that punctures, this main function of the geomembrane, that is uh, this barrier, okay, to act as a barrier, that will fail, right? So we need to protect that geomembrane. So to protect the geomembrane, very thick non-woven geotextiles are generally laid over and below, top and above and below the geomembrane. And also the collection of leachate gases. Okay, so some gases actually develop in the waste mass. So we need to drain that, to collect, and then we need to drain that gas also. Okay, so these geosynthetics also help in that purpose. Right? So what is a liner? A liner is a thick or thin layer having extremely low hydraulic conductivity. Right? So obviously the hydraulic conductivity should be absolutely low, because only if it is low it won't it will allow a negligible amount of liquid or gas to pass through it, right? So we don't want liquid or gas to pass, so to pass through it, so use it, so it should have a very low hydraulic conductivity. Okay. So so what happens in reality, a very low, very minute amount of gases and liquid do pass, but that, because mainly gases, so that amount is actually very very less. Okay. So hydraulic, this is because hydraulic conductivity is kept very low. So compacted clay layer is also used sometimes. So a highly compacted clay layer is actually used as a liner sometimes in place of this geosynthetic material. So that also serves as a liner. And the most common is our HDP, high density polyethylene, or PVC geomembrane layer. It is a sheet of geomembranes. And then we obviously have GCLs. Okay. So there are many type of liner systems. So there are single liner system. These are generally used for municipal solid waste. Then there are double liner systems. These are mainly used for toxic waste, hazardous waste, industrial waste. So in single liner system, there is a single compacted clay layer with or without a geomembrane layer, and in double liner system we have two layers of compacted clay layers separated by a drainage layer and also a geomembrane layer for storage of toxic waste. So geomembrane cannot be a complete replacement as a liner membrane. So just geomembrane we cannot use. We have to use this compacted clay layer also with it. So Ministry of Environment and Forest has given some of these. See, you can see the specifications for single composite liner system and for double liner system. Okay, so for uh, two types of hazardous weights, it has given like for some it has given single liner. If you want to use single composite liner system, this may be the this may be the uh, this one. This may be the desired arrangement, or if you want to use double liner system, this may be the desired arrangement. So you can see second composite, secondary composite liner, then we have digit collection system, then primary composite liner. In between this we have this HDP geomembranes. Again we have collection system, and then above that we have the hazardous. So this layer, so above such a thick layer we have this. Finally we are putting up this layer, we are putting hazardous layer. Okay, so quite a thick protection system is there. Okay, so what are the required properties of geomembrane? So there are some important physical properties. These some of the physical properties we already studied previously. These are same as any other geosynthetic material. So they are thickness, density, melt flow index, then weight, water vapor transmission, solvent vapor transmission. This thickness, density, these all these things you already know. This water vapor transmission we will see today. What is water vapor transmission? Then mechanical strength, this tensile strength, seam behavior, tear resistance, impact resistance, all these we have studied. These are similar to whatever we have studied in case of geotextiles and all those things. Okay. Then endurance properties, resistance against UV rays, biological chemical degradation, thermal degradation, all these things are same as other geosynthetics. So water vapor transmission is little bit new, that we will see. Okay. So what are the tests required? So geomembrane, tensile strength test, thickness, dimension, stability, mass per unit area, permeability, all these things are required. And for soil, what are the tests required? So OMC, optimum moisture content, maximum dry density, and permeability of the soil. These are the important tests that we have to do for the soil and for the geomembrane. And this thickness of geomembrane, we'll see how to get the thickness of geomembrane. It's given here. We'll see that later. Okay. Now let us come to this water vapor transmission test. Okay, so in water vapor transmission test what we do is that actually we determine that how much this geomembrane layer, okay, uh, how much water vapor, okay, is actually passing through the geomembrane layer. Okay, so these have really very small permeability, but even though they have very small permeability, but the permeability is not zero, right? So they allow some amount of gas to actually pass through it, gas or water. So in order to determine how much, okay, how much gas or liquid is actually passing through the geomembrane layer, we use this test called water vapor transmission test. So in water vapor transmission test, there are two ways to do. One thing we can do is that we have a cup, okay, in the cup you can fill the cup with water. You can cover the cup with a geomembrane layer. You can cover the cup with geomembrane, and outside you have air, normal air. So inside the cup you have water, right? That means 100% relativity, 100% relative humidity. Inside the cup you have water, so that means 100% relative humidity. And outside there is obviously lesser than 100%. So what will happen? There will be some diffusion of water vapor from inside to outside. So the loss of water in the cup is actually with time is actually calculated. So here you can see as time increases this weight, okay, this weight inside that cup, weight of water inside this cup is actually reducing. Okay, so initially it was 215 grams. In 40 days time, 0.30 almost 0.30 gram it has reduced. So very less, but some amount of water is coming out, that we have to monitor. Other option is that what we can do is that we can put a desiccant inside the cup. We can put a desiccant inside the cup, and outside there is water vapor. Obviously the natural water relative humidity will be higher, inside it will be zero. So how much increase in weight inside it's happening, increasing weight of the desiccant, that we can measure. So vice versa, this will give the same result. So how is the water vapor transmission this actually represented? We write it. Water vapor transmission is actually given by G into 24 by to A. So G is the weight change, T is the time interval, hours, A is the area of the specimen. Okay, in meter square. Okay, so the unit is generally gram per meter square per day. Okay, this is the basic. Okay, allied to water vapor transmission, allied to this, there are some other properties. Okay, so let me write those down. Allied to this, we have one more property which is known as permeance. So what is permeance? Permeance is given by water vapor transmission by change in pressure. Change in vapor pressure. I will give the definition just a second. Right? Vapor transmission by S into R1 minus R2. So delta P is nothing but the vapor pressure difference across membrane in unit is of mercury. Then we have saturation vapor pressure. Yes, we have saturation vapor pressure at test temperature. Okay, this is also in mmHg. R1 is relative humidity within cup. R2 is relative humidity outside cup. Okay, this is one property, that is permeance. So permeance, the unit of permeance is actually metric parms. Okay, this was permeance. Again we have one more. What is it? Diffusion or permeability. It's given by permeance into thickness of the geomembrane. The unit is metric parm. Okay. Now let us see an example. Write the question here. Calculate. We'll write in short. Okay. We remember this permeability is not normal Darcian permeability. So we will discuss it. Okay. Let's do this one first. Permeance, diffusion. Okay. 0.75 mm thick PVC geomembrane. Area is 0.0030 meter square. Okay. Relative humidity difference is 80% at 30 degrees Celsius. Okay. Okay. So the test data is given in previous slide. That means this one. Okay. So this is the test data. So if you see from here, so you can find out that for in 40 days approximately 0.216 gram weight is lost. Okay, in 40 days time 0.216 gram weight is lost. So if you want to find out the water vapor transmission, we given by 216 into 24 g into t, by t time is 24 to 40 days into 24 hours into area 0.0030. So if you calculate this, 1.80 gram per meter square day. Next we have the permeance. Permeance was WBT by S into R1 minus R2, right? So 1.80 by S. S is the saturation vapor pressure at temperature. So generally at 30 degrees saturation vapor pressure is 32 mm of mercury. Okay, so 1.00 minus 2.00. Sorry, 0.0. Yeah, 1.00 minus 0.20. 80%, na? So it's given. So directly you can add 80% also. So it's given that 80% relative humidity difference. So difference is 80%, 0.80. So you get this as 0.0703 metric bar. Then last we have diffusion. This permeance into thickness. So 0.0703 into 7.5. This will come out as 0.0527 metric per mm. So this this is also called permeability, but this permeability is Fickian diffusion. Okay, this is from Fickian diffusion, not equal to a normal Darcian permeability. Just permeability this K that we find out generally, that is not equal to that, but we can find this out from that only. So let us see how to find that out. For that one, what we need to do generally, what we do, we just manipulate the units. Okay, when we manipulate all these units to actually come to that Darcian permeability. Okay, let us see how to do that. So WVT is 1.80 gram meter square day. Okay, now we have to, if in order to convert it to cm square, meter square to cm square, we will multiply by 10 to the power 4. Okay, then 24 into 60 into 60. This will change to seconds, right? So if we do this, we will get 2.08 10 to the power minus 9 gram centimeter square second. So meter square day we have converted to centimeters. Next is permeance. 2.08 into 10 to the power minus 9 by 32 into 0.8. So it will come out as 0.812 into 10 to the power minus 10. Unit will be gram centimeter second, same, just mm hg. This will come. Okay. Now what is permeability? Permeance into thickness, so 0.812 into 10 to the power minus 10 into 0.075. So this will be 0.609 into 10 to the power minus 11 gram centimeter square second mmHg. Okay, mmHg per cm of liner. Okay, so it will be 6.09 into 10 to the power minus 11. Okay, this mm we converted to cm, so this one came here. Okay, mm to cm, so 6.09 gram cm square second mmHg per cm. Okay, now this mmHg, this is in terms of mercury, right? Mercury pressure. Now that mercury pressure we will convert in terms of water pressure. gram cm square second cmhg by cm liner into 13.6 water by mercury. So this will come out as 0.448 into 10 to the power minus 11 gram centimeter second cm water cm liner. Okay, so mmHg we converted to cmHg, and cmHg then we converted to cm water. Okay, now it came to cm water per centimeter liner. Now we will use density. Sorry, we just add one page. Yeah, so now using density of water, we have hydraulic conductivity is equal to 0.448 into 10 to the power minus 11 gram same cm square second cm water by cm liner water by mercury into 1.0 gram per centimeter cube. So if we now cancel all the units, we will finally get K is equal to 0.5 to 10 to the power minus 11 second. Okay, so this is Darcian permeability or hydraulic conductivity. So just by manipulating the units, we reached here. So this is very fast portion. It is easy to understand. See, up to this gram cm square per second, then you have gram cm square per second per mmHg. This mmHg then we multiplied by length, so it length thickness of liner, so per cm thickness of liner. Then this mmHg is converted to cmHg, and this cmHg is then converted into water pressure. Okay, 13.6. You know the conversion between mercury and water is 13.6, so 13.6. So finally we multiply by the density of water at the denominator, we get this Darcian permeability or hydraulic conductivity. Okay, let us see this. Consider a 7-meter deep geomembrane line pond that is leaking liquid and has rising gases. So both these things can happen, or any one of these things. So it can leak a liquid also, or it can discharge gases also, or it can do both. Okay, generally landfill can do both also. It can leak some liquid also it can discharge some gases also. Okay, the width is 200 meter with a grade downward from left to right as shown. A high estimate of geometry leakage is the maximum high estimate is this much, 5,000 liter per acre per day. The proposed under drain to be used is 6.3 mm thick biplanar geonet with geotextile bonded to each surface. What is the safety factor for this geocomposite liquid? So this is not this liner design. This is from the previous classes. This drainage design. So this is from that part. Okay, this question is from that part, drainage design, but related to landfills. So how much is the flow? Q is 5000 liter per hectare. So this will be equal to approximately 5 into 10 to the power minus 4 meter cube per meter square. So Q is 0.0005 into 200 to 1 is equal to 2.10 meter cube. So you multiply this by the area, you get in meter cube per day. Okay, this we convert to minute. 2.10 by 24 into 60 if we do 26.9 into 10 to the power minus 5 meter cube per minute. Okay. Now what is the slope? The slope is 5%, that is 0.5% actually, 0.005. So now what is the normal Darcy formula? Q is equal to KIA. KI, what is A? Thickness times width. So what is KT? KT is equal to the theta required, specificity required, nothing but Q by I into width. Q is, what is Q? 6.9 to the power minus 5. So we have solved a lot of problems, similar problems, right? I is 0.005 to beat this 1. So we'll get 0.139 cube per minute. Now it is given that this is 7 meter high, right? So 7 meter high, but line pond. This is a pond. Okay, this is a pond, that means water is there. This is water. 7 meter. So 9.1 into 7 meter, that this much vertical pressure is acting on this geocomposite, right? This much vertical pressure is acting on this geocomposite 7 into 9.81, isn't it? So, so corresponding to that vertical pressure 7 into 9.81, that is approximately how much? Vertical pressure to 7 into 9.8, this will be approximately 70 kPa, no? Little bit less. So corresponding to 70 kPa from the design, from the test, from the test data, we need to get that allowable theta of that particular geocomposite. So say from test data we have obtained that the theta allowable is 0.60 meter cube meter. Okay, but then for this has to be obtained from test. Okay, by testing the geocomposite. Now from here finally you can find the factor of safety, theta allow, theta required to 43. Okay, like this we have to do. Generally what happens is that any leaking liquid, any liquid will, what will happen? Any liquid will actually flow like this, down slope, from high slope to down slope, and it will drain like this. And what will happen to the gas? Gas is lighter, okay, lighter than liquid, so it will try to go up. So gas will actually go like this, and it will actually vent out like this. Okay, so both of them generally in a well designed linear system, generally this happens that the liquid and the gas actually travel in opposite direction. Okay. Okay, just a second. before we go to this, uh, hmm, I want to give you this thing. Okay. Geometric consideration. So generally, what happens? Generally, we have a like this landfill system like this. Okay, trapezoidal form having some slope, horizontal to vertical, some slope. So in that case, the volume is given by HLW minus SHQL minus SH square W plus twice H square H cube. So this is the volume of reservoir. H is the average height, that is depth of the reservoir. W is the width at ground surface. L is the length at ground surface. S is the slope ratio, horizontal to vertical. Okay, this is how we define the volume of the reservoir. Okay, so let us see this. Just a second. Just a second. इसका कवर देना. A square area 125 by 125 meter is available. Okay, construct a reservoir to store a liter of industrial process water. Estimated side slope 3 horizontal to 1. What is the required depth? Okay, required average depth. We need to find out the depth. So what is the volume? Volume is a liter is nothing but 60,000 meter cube. Now if you use the previous equation, so what is the equation? HLW. HLL is how much? At ground level, this length, right? Ground level, this ground level length. So that length is 125 by 125. HLW. So HLW minus 3h square minus SH square. S is slope ratio, means horizontal means 3 by 1. In our case, S is what? 3 by 1. So 3h cube L. H square or H? H square, sorry, this is H square. This is H square. L. H square. L, how much is L? Again 125 minus thrice H square W plus twice 2 into 9 into H cube. Okay, this is S square. So 3 square 9. So if we do this, 60,000 square plus 50 H cube. So if you solve this, you get H is equal to 4. So you can solve this. This is cubic. So with the help of any calculator, this engineering calculator, we can solve this, and you will get that the what is depth that we should have, that is 4.83 meters. Okay. Now next we have the thickness of geometry. How to select? Okay, how to select the thickness of geometry? Okay, just fine. Yeah. Actually, I am not that well today. Yeah. So thickness. So I'll just draw it for you once. So generally, the geomembranes are laid like this, right? So this is the base, the slope, and then we have this, and this is the approximate height, right? Right. And here in this portion, we have some normal stress that is acting, maybe to the soil cover, maybe to water pressure, whatever. Okay. And this is the mobilization distance. What mobilization distance you will see. So, and this is inclined at an angle theta. So what happens due to the force, actually this tension, okay, there is some tension in the geomembrane, this T, okay, this tension actually, the vertical component, so this T tension is acting on the geomembrane, right? So how to the geomembrane, so geomembrane is laid something like this, so laid something like this, okay, laid something like this, the geomembrane is laid something like this, so there will be some tension that is acting on of acting on this fabric, right? Always have tension. So this tension will have two components. One is the horizontal component, other is the vertical component, right? This tension is going to have one horizontal component, another vertical component. The vertical component of the this tension, it gets, okay, it gets mobilized along this x direction. So this is distributed in, no, it is not equally distributed. I will show you how it is distributed. So we have this, so tension T, this is what, T sine beta, T cos beta, right? This much normal stress it is acting, okay. This T sine beta, this is actually resisted or mobilized like this, okay, and this is twice T sine beta by x, right? Apart from this, there are some other forces they are acting. One force is the interface force on the upper layer, because geomembrane is there on the upper face of the geomembrane, okay. This u delta, this is acting. If there is water, say at the top, if you have water or very thin layer of soil, then this fu the sigma doesn't exist, okay. But if there is a thick soil layer present there, thick soil cover is there in this place, if there is a thick soil cover, then this will exist. The bottom, again we have we have two more forces. One is low delta, this is friction due to frictional this resistance in the lower layer, and also FLT due to this T sine beta component, whatever this resistance is coming, okay. Okay, due to the vertical component of T, whatever shear component is coming, that is this. So yeah, so if we summate, take the summation of all the forces along x equal to 0, we'll have T cos beta what is Fu, sigma normal stress multiplied by tan u into x plus low tan low into x. And this one will be 0.5 twice 10, because triangular, that's why 0.5, and beta by x into x tan delta low. So these are the shear resistances that balance the horizontal component of the tension that is acting on the geometry. So this T can also be written as, but this T is equal to, what is this T? What is the maximum value of this T? What is the maximum value that geomembrane can take? That is what the allowable stress multiplied by the thickness. Okay, T allowed by thickness. Therefore, this thickness we can tell, hmm, beta sine beta. Okay, this is the thickness. Okay, I will just add one more page and write everything down. Okay, So what is beta? The geomembrane tension. But this does not occur for liquid or thin soil cores. Membrane due to vertical component of T. Delta, all the deltas are angle of shearing resistance. Resistance between soil and geomembrane, whatever, okay, geomembrane to geomembrane, between geomembrane and stencil. Okay. So one more thing, I will give the general ranges also. So what are the general ranges of these values? Sigma n is generally 20 to 100 kPa to 10 meters. Beta is 0 to 60 is 15 to 100 mm. Allow 6000 to 40,000 kPa. Delta U equal to 0 for liquid, 10 to 40 degree for landfill. Okay, for liquid containment is 0, for landfill it is around 10 to 40 degrees. Lower one is 10 to 40 degree. Okay, so these are to be determined from lab tests. Okay, let us see this basic and easy problem. Determine the thickness of a geomembrane to be used in the containment of a 7-meter deep reservoir where the settlement over a backfill collector pipe could result in a 45-degree settlement. This beta is 45 degree. Okay, so what happens? So that is, so see, so we have a geomembrane layer laid like this. So due to some reason there might be some settlement of this geomembrane, right? So this settlement angle This angle at which the settlement is occurring, this is nothing but this beta. Due to this settlement, what happens? This tension comes into play, right? This tension, there is some tension that acts on a geometry, and there are two components of the tension. Based on that, we determine the thickness of the geometry that we need to use. When a geometry is completely straight, there is nothing, no load acting, there is no settlement. This There is no need for this tension to get mobilized, right? But whenever there is a settlement, so you have laid a geomembrane, because some reason there is a settlement. Okay, there is some reason there is settlement in the geomembrane. Some reason. So in that case, what will happen? Some tensile forces will start generating in this geomembrane layer. The thickness should be such that that the geomembrane can hold that settlement. Okay, that means the geometry can sustain that settlement without failing. The main purpose is that we need to choose a thickness. Okay, you need to design the geometry, you need to choose a geometry with a proper thickness such that it can sustain the possible settlements. Okay, it can sustain the possible settlements without failing. Okay, that is without tearing. So everything is given, settlement angle is given, the geometry is a textures LLDQ 8000 kPa, allowable stress is given. It is only a thin soil cover over the geometry, and then it. Estimated mobilized distance for linear geometry is 50 mm. Okay, so directly we'll just use the formula of thickness. Okay, so what is this? What to say? Sigma n. What is the sigma n? What is sigma n? The vertical stress. So what will be the vertical stress? 7 meter, right? 7 meter times, because like this, so right. So water is there above it. So 7 meter high water. So 7 meter times 9.81. That is 68.67. How we came to this? What is the mobilization distance? 50 mm. What will be 10 delta upper? So this is for liquid containment, right? So in the upper phase of the geomembrane there is liquid. So delta is 0. Frictionless, no friction between liquid and geomembrane. So 0. Delta lower. Okay, this delta lower, we'll just choose this one as. So what is given? There is only a thin soil cover and is to be placed. So a non-woven drill punch geotextile is actually placed beneath this. So we will take this as 25 degrees. Okay, this all should be obtained from test. What is the allowable stress? 8000 kPa cos beta minus sin beta 10 delta lower is 25. So if you do this, you will get 3 meter is equal to 0.53 mm. Okay, so I hope this is clear. So how we get, so what happens is that, so generally we say we have made a pond lined, for keeping storing liquid. Okay, we have built some this reservoir for building, so storing liquid, and we have lined this reservoir with geomembrane. Now what happens, if to some reason there is some settlement in this region, there is some settlement in this region. So due to that, so initially it was like this. So if I zoom this portion here, so initially it was like this, but now what happened, there is some settlement. So this settlement angle is nothing but beta. This settlement, there is some tension that is mobilized. right? So we need to design the T considering this settlement. Okay, possible settlement. Okay, so here we can find. So as this is as in this problem, this was for liquid containment. So here there is liquid, right? So here there is liquid. So upper delta is 0, no friction angle. Lower below this we have put some geotextile. So the friction angle between that geotextile and this is taken. The geometry is taken. And for the upper one, we have taken 0, 0. Okay, moment. Now geomembrane in finite slope and infinite slope. Okay, say you have placed a geomembrane in a very big slope. Okay, very vast, huge slope. Okay, so that will be actually considered as a finite slope because very vast slope. Okay, that will consider as a finite slope. So this is the case of finite slope. So first, so what will happen in a finite slope? In a finite slope, you have the weight of the soil mass downwards acting like that. This is the geomembrane that is laid to the weight. What will happen? There will be a normal reaction force to the normal component of the weight, that is n, right? So this will be acting at an angle delta. Okay, this will be acting at an angle delta. It is nothing but the friction angle. So if I want to write the factor of safety, it is nothing but resisting force made by disturbing force. Now what is the resisting force here? Resisting force is nothing but the frictional resistance. And what is frictional resistance? Normal force times friction angle. What is friction angle? Tan of the friction angle, right? Normal force times the this friction ratio, mu. What is the friction ratio? Friction coefficient of friction is nothing but mu is equal to tan of the friction angle. So resisting force n into tan delta. And what is the disturbing force? The sine component of the weight. That is the disturbing force. W sine beta. So the what is n? N is nothing but W cos beta tan delta by W sine beta. So W cancel tan delta by tan beta. This is the factor of safety in case of finite slope. Okay, delta is the friction angle between soil and tube. Okay, then we have the case of finite slopes. This was the case of infinite slope. Then we have the case of finite slope. So there are two cases in finite slopes. In finite slopes, one is that you have a uniform covered soil. So geomembrane is placed here You have the geomembrane, you have a uniform thickness covered soil, okay, like this. And other case may be, this is the geomembrane, the cover soil is tapered, okay. This thickness is actually not same, okay. This is this case. So for these two cases I will actually give you. For the first case, finite slope and uniform thickness. For that, so actually what happens is that this is the slope, right? This is the slope. So what happens, a passive wedge actually develops here, active and this passive pressure. So there will be some passive pressure acting here, there will be some active pressure acting. So if we equate all this, equate all those things, what we get, we can get the weight of the active, total weight of the active wedges, gamma h square to this Na. So Na, you can see this normal force, okay. This is Na. This Na is given by and weight of the passive wedge is given by gamma h square. Okay, so there is a active wedge formation and here we have a passive wedge formation, okay. And there is a tendency for this to slide downwards, so we need this normal forces also Na, there is also this Np acting. Okay, so if we equate all the forces in the vertical and horizontal direction, we will finally obtain the desired equations. So you got Wa, Na, Wp. The factor of safety is given by minus P plus C by 2IC. Now what is ABC? ABC. What are ABC? A is WA plus beta. B is, okay. I'm not getting into the derivation. I'm just directly giving you all the results. Because the derivation is a little bit lengthy. CA times sin beta cos beta times C plus B. C is A delta CA square beta. WA is what? Total weight of active wedge effective normal force to the failure plane of active wedge, and this is same to the passive wedge. Gamma is unit weight of soil cover, H is thickness of the cover soil is length of slope is so okay, this delta is interface friction angle, CA is adhesive force, C is just a second. Adhesive force between cover soil of the active wedge and geomembrane adhesion between cover soil and the active soil same okay, this is adhesive force, this is the adhesion, another thing so I give okay. So let us see this. Okay, this simple problem. Before this, let me do one thing. Let me give you the other formula also. This is for tapered cover. So geomembrane is placed. The geomembrane is covered by that soil. Okay, the stability of that soil we are finding out. Stability of that slope we are finding out. For tapered cover, all this L, D, everything is given in the figure. So if you see the figure, you will understand everything. Same in this case also, but just the definitions are a little different. So quite lengthy, right? let us see this. Directly just we will put the values na and find everything out. Given a 30-meter long slope with a uniformly thick covered soil of 300 mm, a TU rate of 18 kN per meter cube, a soil has a friction angle of 30 degree and zero cohesion, that is sand. The covered soil is on a geomembrane. Direct shear testing has resulted in interpret friction angle between the soil cover and the covered soil and the geomembrane of 22 degrees and zero addition. CA is 0. What is the friction vector of safety value at the slope angle of 300 to 1 vertical, that is 18.4. So directly just we will put everything in the formula and find what was WA. So this is the case of uniformly thick cover. Okay. So gamma H square then beta by 2. So gamma is 18, H is 0.3 square, L is 30, H is 0.3, beta is 18.4, beta is 18.4. So if you put all the value, you will find 1757 per meter. Okay, then we find out Na is nothing but the cost component. So weight is acting downward to the cost component as weight like this. So the cost component WA cos beta and weight of the passive wedge so twice beta, twice 18.4, 36.8, 27, 2.70 or 270. I will just find it out. 18 into 0.3 squared divided by 2.7. Then find out ABC. I will just give all the values. You can do this by yourself when you do. So it will come out as 40.8. B very big formula. If you do, it will come out as 21.4. C again, if you do, vector safety equal to 21.4 minus B, right? Minus B, the minus plus minus 21.4 B square minus 4 into 14.8 into 3.46 2 into 14.8. Yes, 1.25. Okay, we have here 1.25. Now say uh, we consider a infinite slope. Say the slope is infinite. Then what is the vector of safety? Simply this tan. How much? What is this one? Delta. Okay, delta. What you can do? Uh, delta. They have assumed at 23.4 by 10. 22 degrees. Sorry, 22 degrees is the angle, right? 22, 20, not 23.4. It is 22. And what is beta? Beta is how much? 18.4. So how much will the factor of safety? Right. So if you consider the slope as a infinite, you can see that so the vector of safety is a little bit lesser. Okay. Now one more problem, same problem, but it will be tweaked for this one, our tapered slope. So given a 30-meter long slope with a tapered thickness cover of 150 mm at the crest, extending at an angle of 16 degree to the intersection. That angle omega, which I wrote in the that omega angle. If you see the figure, actually it will be clear. This is the angle omega. Okay, here this is the angle omega. Okay. Same problem, just for a tapered slope. All the values are given. So I will just find everything first. Y 10 omega is how much? 16. Will come out as 128. Then similarly put the formula for WA. This will be like this. You put the formula. Your WA is 390 kWh per meter. WP gamma by 2 10 omega. Check these values, okay, by doing ourselves once. 65.1. Then again A will come out as 37. So here we will get a greater than 1.25. So if we you are seeing that if we use the tapered thickness, right, tapered thickness soil cover, the vector safety actually increased from 1.25, it increased to 1.5. Okay, so for the constant thickness it was 1.25, constant thickness soil cover it was 1.25, and if you are using tapered thickness soil cover it increased to 1.55, right? Now we will see this run out and anchored trench. So uh, so run out is nothing but say you have placed the geometry in a slope. You place a geometry in a slope, and then you have you have the straight horizontal portion, right? You place a geomembrane slope, and then you have the horizontal portion. Above that geomembrane, you have actually covered it up, place some soil cover, right? So you place some soil cover above it. Now you need to actually find out this this length. Okay, what to say? This runout length L R naught, which is this. You can see in the figure. This this particular length. Okay, this is what we need to find out. This is one case when we can just keep the geomembrane straight. Other thing which is possible is that we can anchor the geomembrane. Okay, so we place the geomembrane. So this is slow, this is slow, this is straight up. Okay, this is slow, this is straight up. Okay, slow, then straight, and what we can do, this place we can, so above this we are placing soil cover will be there, and this portion what we can do, we can anchor it into a trench, and then fill the trench with soil, so we can anchor it. Okay, we can, what we can do, we can anchor this portion into the soil. So if we do that, what will happen when a tensile force will be active on this geomembrane like this, when load will come on the geomembrane, so tensile force, so this geomembrane that is stuck into the anchor trench, so what will happen, some active and passive resistances will occur. Okay, active resistance due to what, resistance, active resistance from the soil that is filled in the trench, and the passive resistance of the initial the original soil that is present here, right, from this side. So those two, these active and passive forces, these two will also come into. Okay, here you can see this thing. So this is one more case. So both these cases actually you will see. The first case is for the, that's the run out. Okay, so run out section, if we summate all the forces about x equal to 0, T allowable, the tension, the cost component of the tension, that is the horizontal component, same to the thickness thing. Okay, almost same to the whatever you did in the thickness. What is this one? Upper means normal stress, tan delta upper into L run out length, same. Okay, right, almost same to that. Lower L R naught plus this LT is due to the vertical component of the tensile force. Okay, similar to the previous one, the case of thickness, so I won't write all these things directly. I will write, I won't give the definitions of all the terms because those are almost same. So okay, So what is this T allow? T allow is same as before. T allow is nothing but sigma allowable stress into the thickness. Now in case of runout for trench, okay. I'll just give you same summation fx equal to 0 minus pa plus pp. So these two just forces, these two forces, the active and the passive pressure, these two are the extra forces that will get developed. Okay. So what is pa? Half gamma dat. Dat is gamma dat. Gamma a, sorry. Not me write dat. Gamma 80 means the soil inside the anchor trench, the unit weight of the soil inside the anchor trench, times the depth of the anchor trench, times Ka, that is the coefficient of active earth pressure of the soil in the anchor trench, to Dat. Dat is the depth of anchor plus sigma n Ka T P Pa is equal to 0.5 gamma 80 and Ka. Similarly, Pp half gamma 80 Dat plus sigma n plus Kp, that is the passive earth pressure coefficient. Okay, just these two terms. Okay, just these two terms are added here in this case. Others, everything will be same. Okay, what we can do is that we'll just I did not write that down. I think. Okay, I will just directly write the problem down. Okay, example. Consider a 1 mm thick LLDPE geomembrane with a mobilized, it is the maximum allowable stress, it is a T allow of 5000 kPa, which is on a 3 horizontal to 1 vertical slope. Determine the runout length to resist this stress without use of a vertical anchor trench. Use 300 mm cover soil of gamma 16 parent per meter cube and phi 30 degree. Okay, so let us do this one. Same, just directly we know everything. So what is T allowable? Allowable stress times thickness. How much is the allowable stress that was given? 5000 kPa. So 5000 into a thickness was given as 0.1 mm. 0.1 mm means 0.001. Uh, 0.001 meter will come out as 5 kilonewton per meter. Okay, now are not T allowable by cos beta minus sin beta tan delta L by n tan delta U plus delta L. So 5, this is 5 kilonewton per meter. Cos beta, what is beta? 3 by 1 means 18.4. 10, 30 degree friction angle. But I will, this is not phi actually. Friction angle with the, this is the friction angle with the geomembrane. Okay. What is the normal stress? Normal stress is 16.5 into the thickness of the cover soil. This is 0.3. 300 mm. 300 mm means 0.3 meters. Okay. So why we are taking this upper tan delta U? Tan delta U is 0. That is because the upper soil is thin. Okay, thin layer of soil, just thin layer of soil. See, that's why the delta U they are taking as 0. Okay, delta U they have taken as 0. To 0.86 comes out as 1.34. Now, just a second. We have time, right? So we can solve one more. So this one was without trench. Okay, now with trench, if you want to solve, say we are using a trench. So that case one which will say I will just directly take, say thickness is given as this, run out length is given is say 1 meter. Okay, allowable stress is 16,000 kPa. Covered soil thickness same as before, 300 mm. Gamma unit weight of soil 16.5 kilonewton per meter cube, and this soil is only placed in the trench also. Okay, so same properties. Other properties are same. This 30 degrees also same. Friction angle of the soil to the geomembrane, and phi of the soil is 35 degree. Delta is 30 degree. Okay, so T allow again will be T allow into thickness. So sigma allow is 18,000 into 10. We want to do Fu delta. So F upper you can take this as 0, because we are assuming that the soil layer is thin, covered soil layer is thin, and there might be cracks that develop. Okay, that's why we are considering this into this will be 0. Same, okay, same as before, just without directly using the formula, we are writing all the terms separately. 0.3 into 16.5, this will be sigma and normal stress. 16.5 is the unit weight, 0.3 is the thickness, 10 delta lower. And what is LR naught? LR naught, let us keep it. Why, I will tell you. Sine beta, this will be 24, 3 is to 1, so 18.4, 10 T. Now PA, 0.5, depth of trench we have to find out. K, what is K? 10 square, 45 minus 5 by 2. So if you do this, it will come out as 2.24 T square PA PP. KP 10 square. Let me write down the formula. KP is how much? 10 square, 45 plus 5 by 2. 45 by 2. Now, what was the basic equation? So, equal to 0. 24 into cos 18.4 is equal to 0 plus 2.86 LR naught plus 4.37 minus 2.4 t square t minus 1.34 t t plus 30.4 t square t plus t.3 t. So let us, if we do this one, we will get 2.86 R naught plus 17.0 t is 2.28 square kt. Now, see, it was given that for 1 meter LR naught, we can get the DAT. This we can do. Other thing what we can do is that we can take, we can prepare a design chart. Design chart, how design chart? We can take various values of LR naught to get various value of this DAT. Also, what we can do, we can change the allowable stress of each geometry. Okay, T allow. So if we change the T allow changing means what? We are changing T allow means what? We are changing sigma allow changing means what? Different geometries will having different allowable stresses. Allowable stress means what? The maximum stresses that a geometry, particular geometry can take. So what we can do, we can vary all these three things: LR naught, DAT, and this T allow, the allowable tensile strength, the tensile stress. All these things we can vary in order to get a design chart. Okay, first let us see that for LR naught equal to 1 meter, how much DAT we are getting actually, how much depth of trench is actually required. So if we solve this, this DAT approximately will come at around 0.57, so we can take it as 0.50 meter. Okay, so for if we take the length, this run out length as 1 meter, then we are getting this depth of trench as 0.5 meter. Okay, now what we can do is that we can make a design chart. So what we can do, we can vary. So say for T allow, uh, say for the, so one thing we can fix, and let's say we are fixing DAT as some say 0.5, right? So 0.5 we are fixing, and then what we can do, we can vary this LR naught and this T allow. So here many values you will get, then again you can change the DAT the depth to say 1, then again we can get like this, again we can get, so like this we can get many values. So after that finally what we can do, we can make a chart. So in here we can have LR naught in meter, here we can have T allow in kilonewton per meter. So some we will see that we are getting some graph like this, like this, like this, like this. So this is for DAT is equal to 0. This is for DAT. These are straight lines. Okay, not curve. I will draw this again. That's right. See that you are getting certain straight lines. This one is DAT 0, DAT 0.1 meter, DAT 0.2 meter. Like this, you can get some design chart. So say now you have you know that you have to use this geomembrane, and this geomembrane has a allowable stress of this much. So you just go to the chart. Okay, my geomembrane is this much T allowable. For that, if I use a DAT of zero point 0.2, if I choose a depth total is zero point 0.2, I have to use a runout length of this much. And if I decide to use a depth of trenches say this much, then runout length is this much. They say if I decide that I won't have any trench, then I will have this much. So like this, you can choose. So that way, your task will be our task. The designer task will be easier, okay, for future work. So like this, what you can do, we can make certain design charts, okay. Okay, okay, one more thing I wanted to one more thing I will give you. So we already solved this in this finite slope cases where the slope, so geomembrane is there, soil cover is there, we found out the soil cover is there, we found out the factor of safety, right? Geomembrane is there, soil cover is there, we found out the factor of safety. Now for some reason, if say your factor of safety is low, you want to increase the factor of safety. Okay, what we can do is that in that case what you can do, you can put some geogrid reinforcement here. Okay, you can put some geogrid reinforcement. In that case, how what will happen, the tensile strength of a T force coming from the tensile strength of the geomembrane, the geogrid, that will be an extra term that will be coming into the previous equations. I will just give you that equation directly. It's very easy to understand, you can easily drive it. I will just give that to you directly. Okay, just a second. So this WA, if geogrid if geogrid reinforcement is used in slope with geomembrane, in that case WANA WB same, this will remain same as previous, this won't get affected. This EA term, that is the earth pressure, actually gets affected, and that's why this ABC terms get changed. This A will change into this T term is coming here. Okay, this T term, and this one will be same. not unaffected. So this T is coming here. Okay, this T is coming here. What is this T? T is the nothing but the T ultimate by the cumulative direction vector of the geogrid. Okay, this change will just come there. Okay, other all the things or other all the things, these are all the things will be actually same. Okay, all the things will be same. That this T will be coming to the picture. Okay, so with this we will end the last and the final live interactive session, and tomorrow there will be summary session at the morning 8 a.m. If possible, you can attend. There will be a summary session of 1 hour duration from 9 a.m. to 10 a.m. 18th October, that is tomorrow, from 9 to 10. Just we will just revise whatever you have studied in the 12 weeks. We won't solve any problems and anything. We'll just recall just casually. We will just go through all the topics that you have covered in these 12 weeks, in these 3 months. Okay, so thank you very much for attending, and if you have any query regarding anything, please feel free to contact me anytime. You can write to me anytime at any point of time if you feel the need to. And I hope that this course was enjoyable too, and you learned something out of this course. My duty was just to try to solve some problems and just to help you revise whatever was discussed in the basic in the main lectures. Okay, so tomorrow morning 9 a.m. if possible, if anyone is free, they can attend. Tomorrow morning 9 a.m. we will have one last summary session of 1 hour duration from 9 to 10 a.m. and then we will wrap up this course. Okay, so thank you for attending. The link for tomorrow session will be same as today's link only. Okay, so tomorrow 9 a.m. just a normal general summary session we will be having, just a casual discussion regarding everything from the first to the end. All right, so with this we will end. Just before end, just we will see what once we will just see whatever we have done today. So first we just studied all the whatever, what are landfills and what are the liners. We just saw these things. We saw what is vapor transmission test. We saw what is PPT, how to determine water vapor transmission. Then we saw what is permeance and all those things, how we can transfer the Fickian permeability. This is the Fickian diffusion to our normal Darcian Russian permeability just by changing the units. Okay, then we solved some problems regarding that. Then we saw how to actually get the thickness of the geomembrane, how to decide the thickness of the geomembrane. That we saw. Then we solved one problem regarding that. After that, we saw the factor of safety of the slope. Okay, the slope of the say landfill. Right? So how to determine the factor of safety? Infinite slopes, finite slopes. Infinite slopes, there were infinite slope and finite slope. Infinite slope, there were two cases: covered uniform covered soil, tapered covered soil, that we saw. And if you want to increase the more, if you want to increase more the factor of safety of this, you can use a geogrid, that we saw how with the help of geogrid you can increase the factor of safety more. That we saw. Then we, yeah, that was it. And then we at the last we discussed about this run out length and the end curtains. Okay, so with this we finished our discussion, and tomorrow just we will have a casual summary session at 9 a.m. in the morning, just for 1 hour duration, where we will casually discuss, not solve any problems, just casually discuss this 12. I will just recapitulate these 12 weeks within 1 hour, just discuss whatever was taught, and then we'll finish it. Okay, so thank you for attending, and have a good evening. Okay, so thank you.